So it's a pleasure to have here Christian Gogolin talking about quantum many-body systems and how to understand them with machine learning tools and also to use them as new machine learning tools. Please go ahead. Thank you.
Yes, thank you very much. I've enjoyed the first day of the meeting and also this morning session tremendously. And yeah, I must say that I was actually a bit flattered and actually fairly surprised to receive this invitation to not only participate, but also to talk about some of my past work during this meeting, because well, I'm certainly very interested in this crossover between machine learning and quantum physics, but I wouldn't necessarily maybe consider it my main research topic. So I'm enjoying this very much, and yeah, thank you for the opportunity to speak here. And yeah, even more so maybe because, yeah, while I have worked in academia for some like almost 10 years, and I have worked with the people at Xanadu for some time on quantum machine learning topics, I have actually slightly over a year ago moved to an industry position, and I'm now working in the digital R&D department of Covestro. Covestro is a big German chemicals company and one of the largest polymer producers of the world. And yeah, you may also, speaking about affiliations, you may also know me as one of the 3 founders of the Quantum Journal, which of course publishes some of the results that are relevant for the kind of research in this workshop. Then that's probably also the right moment to say that today I'm not speaking as a representative of any of those 3 organizations, so neither as a former collaborator with Xanadu, nor as a current employee of Covestro, nor as a representative of the Quantum Journal. I'm giving this talk as a scientist, which is also why I'm using my private slide deck style and not the Covestro company slide deck style. Yeah, I should say that. Then, yeah, coming to the outline of the talk, I very much like that this workshop takes seriously that quantum machine learning can be understood in like 2 different ways, of like using machine learning tools to better understand quantum systems and to use quantum systems to do better machine learning or optimization. And in the main part of this talk will also consequently consist of 2 parts. One which is on using machine learning to understand quantum many-body physics, and the other is on like software to more efficiently do research in this area of quantum machine learning. So and then, well, when I originally thought about what I would be talking about, it wasn't clear whether some recent results which have now appeared in the archive would actually be published before this workshop. Now they are. So I will also, as in the very beginning, spend a few words on some recent results, which I hope are also relevant for this audience here. And I should say that because I want to kind of rush through this initial part a bit, I'll be using quite a bit of jargon and assume a lot of prior knowledge. So don't worry if you somehow get lost a bit in this first part of the talk, depending on what your background is, because the background of the participants here is very broad. Then you will be rewarded by, I would say, very shallow and like for many of you, or some of you actually, fear almost trivial second part of the talk, where we'll be talking about machine learning quantum systems and software for quantum machine learning. Okay, but let's get started. First, some words on like 2 recent papers from this year with relation to the theme of this workshop. And the first is joint work with David Wierichs and Michael Castellano that was started when all 3 of us were at the University of Cologne. And it is about choosing good optimizers to optimize variational quantum eigensolver type variational quantum algorithms. And the I guess main results can be summarized by showing these 3 plots. So I'll walk you through this slowly. So what we are trying to do here is find the ground state of the transverse field Ising model. And we chose the transverse field Ising model because, being exactly solvable, we first know what the true ground state energy and the true ground state is. And the fact that the model maps to free fermions allows us to go to very large system sizes and do extensive statistical numerics for very large system sizes, and consequently also ansatz with many parameters. And that that turns out to be crucial, because some of the intuition you might draw from small systems turn out to be false when you go to larger systems. And then what we're doing here, we're comparing 3 optimizers, BFGS, which is the by far most widely used in the VQE literature today, Adam, which is probably the algorithm of choice in the classical machine learning, and then the quantum natural gradient optimizer that we've also already heard about yesterday. And the 3 plots, so the first plot is the energy gap after the optimization finished from the true ground state energy. And you can plot it versus the system size. And you can see that, while BFGS somehow works reasonably well for small system size, it starts to get problems for intermediate system size. And then there's this sharp transition around system size 2022, where the majority of the runs fail, and you actually get stuck up here in a state above the energy gap of the system, and BFGS doesn't find the constant energy anymore. Things for Adam look a bit better first. It like really converges well for small systems, and then but then also like more and more runs start to fail and somehow not converge, and or even get like fully stuck here. And then there's NatGrad, quantum NatGrad, which just like nails the ground state energy for all system sizes that we could access. The second interesting figure to look at is the number of epochs the optimizers need. And here it's interesting to look at NatGrad. It's interesting to look at Adam, which had a reasonably good performance in terms of accuracy, but you can see really the number of epochs needed for convergence shoots up. At least polynomially, with the system size. And then here, those are runs which were interrupted because they were like after 50,000 epochs, they had still not converged. BFGS converges fast, but then you get those convergence problems here. And NatGrad, also grows, but at least in a much tamer fashion than NatGrad. And so you say, okay, look, you really can't draw conclusions from the fact that, for example, BFGS is known to work very well for small VQEs. You really may need a more elaborate optimizer like NatGrad if you want to solve VQEs that have a chance of actually giving you a quantum advantage. Now, what you pay for that is what is shown here in the right graph. This is some time estimate for how much it would take to do those optimizations on a real quantum computer, because NatGrad, to actually use NatGrad, you need to measure the Fubini matrix, and this is a quite expensive operation if you want to do it exactly or like with reasonable precision. And consequently, you can see here that NatGrad becomes quite costly. But then if the alternative is to not converge at all, then maybe this is what you have to do, to like pay for convergence. Maybe an interesting side note here, the block diagonal approximation to the Fubini matrix, which was proposed in the original NatGrad paper, it doesn't work well here. So first, the Fubini matrix in the ansatzes that were used here, which are Quawa-like, are not at all block diagonal. And then if it forces it to be block diagonal, then the optimization doesn't work so nicely anymore. And there's like more results also beyond the transverse field Ising model in that paper. Great. Then the second thing I want to quickly mention is a result that really came out of my work here at Covestro, where I'm part of the digital R&D and consequently can talk directly to chemists who use computational chemistry tools in an industry setting. And out of this collaboration with Jose Gomez and Vincent Elfring, who is from Q&Co, came this paper here where we are kind of drawing intuition from ansatz from the classical computational chemistry literature to come up with a much more NIST-compatible VQE for chemistry. And the underlying idea is very simple to understand. Instead of treating the electrons of the system as individual fermionic particles, it is an approximation, or a widely used approximation in computational chemistry, to use those to treat those particles as paired electrons. So this is used a lot on the self-consistent field level when people do restricted Hartree-Fock instead of Hartree-Fock, and consequently we call this here the restricted approximation, or the paired electron approximation, or the doubly occupied, or the seniority zero approximation. It has many names. And while making that approximation in post-Hartree-Fock methods, it does reduce your computational costs. So there's like a paired electron version of full configuration interaction, so of exact diagonalization. There's a paired electron version of coupled cluster, and so on. And those are more efficient than their like full fermionic counterparts. It doesn't really dramatically reduce the computational complexity. So, for example, this doubly occupied full configuration interaction still scales exponentially with the system size. But if you want to do this on a quantum computer with VQE, then your life gets much easier. So because you now have bosonic particles, you don't need to use Jordan-Wigner anymore to map your fermions to spins, but you can directly map the hardcore bosons of this bosonic model to your qubits, which is much easier. You get a Hamiltonian that consists of just two non-commuting terms, so you can measure like all the Hamiltonian terms with, I think, actually just 3 different measurement settings, and you can and also like a unitary coupled cluster type ansatz, which is essentially a Trotter step under that Hamiltonian, becomes much shallower, and it can be like nicely combined with a swap network. So you can there's like very short VQEs that require very few measurements, which essentially give you a precision that is on par with this doubly occupied full configuration interaction. And just showing this here. So only look at the, in that plot here, look only at the orange and the violet curve. The violet curve down here, this is a more or less exact solution, full CI and a very large basis set. And then you can see here that if you do standard unitary coupled cluster, but in a very small basis set, that's the red curve, you're actually making a quite huge error. If instead you're using this restricted approximation, but then you invest the qubits that are freed up, because you only need 1 qubit per mode now instead of 2, to go to a larger basis set, you can actually get results which are closer to the ground state energy. And also the convergence of the optimizers is like speeds up quite dramatically. You can see here that converges in, this is an exponential scale, that it converges on like 2 to 3 orders of magnitude faster to the final energy training that VQE than training the unitary coupled cluster VQE. So of course, this is like not expected to be useful for precision chemistry of small molecules, but this approximation does seem to have some potential applications in like bond breaking chemical reactions of large molecules. And at least it's a systematic way to improve upon Hartree-Fock. Yeah, so this is just combining some ideas from classical computational chemistry with quantum computing. Good. Then let me come to the main part of the talk. And because this is kind of not really my subject, I thought it would be nice to say why I am nevertheless very much fascinated by this, and why I think this has a great future. This topic of applying machine learning tools to quantum systems. Well, first of all, there is big data, right? The exponential curves of quantum many-body systems somehow suddenly becomes an asset, because it's easy to produce large amounts of data, and actually everybody can do it. So we can do meaningful research on those things, even if you're not Google or Amazon. This data usually has structure because it comes from physics problems. but it's often very hard to use or extract that data with conventional methods. And I think we've like seen beautiful examples of that in the talks of this workshop. And well, then, okay, ultimately, these machine learning tools are heuristics, but people in physics and chemistry are very much used to heuristics, so that's fine. The applications are not safety critical, right? If you misclassify a phase transition, then nobody dies. And classification and control problems are really everywhere in many-body physics. For example, and that's maybe the prime example, is when delineating phase transitions. And of course, there's no surprise here that this was one of the first problems people looked at with say, supervised learning tools for phase transitions, where you could calculate an order parameter, and then you can obviously kind of train a neural network to identify your phases. And we thought that that was a little bit too easy, and we would rather want to try to use machine learning in a setting where there was a chance that it would actually give an advantage over classical attempts to understand what was going on physics-wise. And that was the starting point of this paper here, done at my time during my time at ICFO with Patrick Humbelli and Alexandre Dauphin and the fortunately now deceased Peter Wittek on which we called automated discovery of characteristic features of phase transitions in many-body localization. So as I cannot assume that everybody here is familiar with many-body localization, like one slide on many-body localization. So we start from the Heisenberg chain, which simple spin model looks like this. The Hamiltonian wants to make neighboring spins aligned. So the ground state is like all the spins in one direction. And then the excited states, they look more or less like this, like spin waves. So we want to have near, like spins close by, kind of pointing in similar directions. Okay, so now what you can do is you can add a random field in z direction, where these local fields hi here are chosen, say, from a Gaussian distribution or from a box distribution. And then if that field here is very strong, then obviously the eigenstate just align, or the ground state just aligns with that field, and then the excited states are just also diagonal in z base, and they look like this. Yeah? And then it's clear that if you ramp up that field strength, at some point there must be a transition from a phase where the eigenstates look more like this to a phase where the eigenstates look more like this, and this phase transition is called the many-body localization transition. So this has been studied extensively, and there's been like a huge body of literature accumulated over the last few years on this topic, and extensive numerics. So what you're seeing here is the as a function of the energy. So here we're going through the spectrum. So down here is the ground state, and then here come the excited states. And a function of this, the strength of these local fields, you can see in which phase you are, and you can see that like different parts of the spectrum localize at different field strengths. And then those different points here are, I think, 5 or 6 different order parameters that people came up with to describe this phase transition. And all of those order parameters are non-local, so they don't fall into this Landau paradigm of order parameters. There's no complete agreement on what the best order parameter is. You can see that if you do like finite size scaling estimates, as was done in this paper here, they do not agree within error bars. And that's probably because there's very strong finite size effects influencing that phase transition. And then to obtain such a plot, like for each point in the graph, people had to do something like 10,000 disorder averages. So you draw 10,000 realizations of the Hamiltonian, diagonalize it, compute those quantities, and then do that for different system sizes and extrapolate to the thermodynamic limit. So it's a huge pain. And so the question was like, can machine learning come to the rescue here and somehow help us understand those systems better? And the idea we came up with is based on a model that's called domain adversarial neural networks. So the way this works is that you're drawing states from different regions of the phase diagram, and you're feeding them through a convolutional neural network. And then the output of that network is interpreted by 2 other neural networks, a phase discriminator, which tries to guess which phase the state that you used as an input came from, and an adversarial, which tries to guess essentially whether the state came from deep inside the phase or from somewhere else. So because the way you're generating those states here is you can only label states that are deep inside the phases, because we don't know where the phase transition is. That's what we want to learn. But states that are deep inside the phases, we can be pretty sure that those are of that phase or of that phase. And then so we draw states from deep inside the phase, and then we draw states from also in between, closer to the phase boundary. And this guy here tries to guess the label, and that guy here tries to guess whether the state is labeled or not, so to say. And then you do error backpropagation, adjusting this convolutional network here, such that the task of this guy here becomes as easy as possible, and such that the task of that guy here becomes as hard as possible. So you're doing error backpropagation by inverting the sign when you backpropagate those errors into the network here. And so there's this adversarial effect here of these two competing neural networks, and the effect, or the overall effect, is to do this, you don't need to know where the phase boundary is, and no, why is it jumping around? Sorry. And you don't need to do any manual feature engineering, right? We are really just giving the neural network the states, and we're not pre-computing any order parameters. We're not telling it, so to say, what the physics should be. It's supposed to figure that out on its own. And the effect is that the network tries to put the boundary, so to say, at the position where the states change qualitatively. And that's, I think, what should be the phase transition point. Okay, and then you can compare that with other ways of estimating the phase transition. And so I'm showing here data. First, maybe have a look at the background of those two plots. So the left is the background, is the output of the neural network. The output of this classifier neural network, and the right is the order parameter computed as a function of the average adjacent gap ratio, which is one of the commonly used order parameters. And you see already that that here was averaged over just 50 realizations, and here also over 50 realizations, that the data on the left is much less noisy. So it should be much easier to extract a phase boundary from the output of the neural network than from the data you get when you compute this average adjacent gap ratio. And that's not so surprising, actually, because you have a lot of information in those eigenstates, and then here you're computing this one number and you're throwing away everything else, whereas this neural network really looks at the state in their entirety, and so statistical properties can be much nicer. And then, to substantiate that, the data points here are the extrapolated phase boundaries and uncertainties from this domain adversarial network from just 500 realizations. And then in that paper that I showed earlier, they used actually, well, for all system sizes, 10,000, except for the largest, for which they could only afford 1,000. And those are two of the different order parameters that you find in literature. So you can see that from just 500 realizations, we get error bars which are comparable with the disagreement between different order parameters for 10,000 realizations and larger system sizes. Yeah? So you really see that you can profit a lot, in the sense that the statistical properties get much nicer, and you need to diagonalize 2 orders of magnitude fewer Hamiltonians in order to get a same uncertainty about the position of the phase boundary. And I think this is kind of cute. Superior statistical properties, vastly less disorder averaging. Good. Then I want to come to this second part, software for quantum machine learning. And again, some motivation. So I think this is probably going to be one of the first relevant applications of quantum computing, because, we had this question yesterday, right? So why is VQE better? Well, nobody knows whether it's actually better, but there's a good chance, because it unlocks objective functions and, for example, kernel methods, kernel maps, that classical computers simply cannot calculate, there's a good reason to hope that no error correction and fault tolerance is needed in your quantum computer, because the learning of gate parameters may compensate a lot of the imperfections of your device. And then some quantum many-body or chemistry problems map very naturally to quantum hardware, and they're extremely hard sometimes for classical methods. So there's the prefactors here just look very favorable for quantum computing to outperform classical methods. There's been immense progress on the algorithmic side in recent years, and I think it's getting much easier to get into this field, because there's now very nice software to do the training and optimization design of such quantum neural networks. And one such software is Pennylane, that I've helped develop version 1.0 with Xanadu. And the underlying design principle there is that of hybrid quantum classical computations. So you think of a quantum compute node as a function that would take some classical input and produce some classical output, f of x, plus some angles that were set to like fix the parameters inside of that thing. And you can embed or combine such quantum nodes in a seamless way with classical nodes into some computational graph to compute some output, right? So that guy here would be the final output you're interested in, and takes as input the output from here and there, and so on. And then what you want to be able to do is typically to train such a like all the models in such a graph. So you need to be able to do error backpropagation through that graph and adjust those parameters. And and that's what Pennylane does by sort of telling your automatic differentiation tools how to differentiate quantum nodes. And why is that even possible, right? It's not even clear a priori that you can do this, but turns out that for many quantum circuits, this is kind of very nicely doable, because as it turns out, this gradient of the output function with respect to this parameter theta at fixed x can be written as the difference of evaluating that same circuit with the gate with respect to whose parameter you're trying to differentiate just shifted by some finite non-infinitesimal amount and in one direction, and shifted by the same amount in the other direction. Yeah? This is not an infinitesimal difference, but that's actually a finite difference. And I don't think I have the time to go through the maths. And it's probably also, anyway, for this audience, not so relevant. So you can show quite easily how to derive this parameter shift rule, it is called. And and so the bottom line is that if you have a quantum computer that can compute your objective function, your expectation value of some observable beta, of some observable b, then you essentially already also have a device that computes the gradient of that b with respect to, okay, sorry, it's now called mu, that should be theta, which is just a difference of two valuations. So you can use the same quantum hardware to evaluate the gradients. This works straightforwardly for all parameterized gates that are single qubit Pauli gates or Pauli strings, or more generally any gate that has just two eigenvalues, or whose generator has just two eigenvalues, and then there are like generalizations of this. All the other gates in the circuit can be completely arbitrary, and there's also generalizations which we derived in the paper for Gaussian continuous variable gates, where there's like similar parameter shift rules for certain gate classes. And well, your estimate of the gradient, if you compute it in this way, is much more stable than if you would want to do a finite or infinitesimal difference estimation, because then you would have a noisy quantity here that differs very little from a noisy quantity here that you're dividing by a small number, and that's a very bad idea to estimate your gradient, whereas this thing up here is statistically much more stable. So that's really the way to go. But then you need, of course, some software to construct those circuits for you, because you don't want to do this by hand. And this is what Pennylane essentially does. It's a library for quantum optimization, machine learning, that is built exactly for such hybrid quantum classical computation. It enables optimization of such like whole hybrid computations via automatic differentiation, and actually does that with your interface of choice. So you can use it with plain NumPy through a library that's called Autograd, which essentially like punches auto differentiation into, or like pushes auto differentiation into NumPy or puts it on top. But you can also use it with more common machine learning frameworks like PyTorch and TensorFlow. It's open source and extensively documented. So I think actually it's a great resource for students getting into that field to just work through the documentation of Pennylane. After that, they will very much, so to say, know what a VQE is and what quantum machine learning is, and where the problems are, or the interesting questions are. And it's not only open source, it's also hardware agnostic, extensible via plugins. There are plugins available for the hardware of several big hardware providers, IBM and Rigetti and Google's Cirq. There's recently been a plugin developed by Alpine Quantum Technologies for their ion trap quantum computer. You can use all the simulators from those different frameworks. In addition to that, Project Q and the CV quantum computing simulator Strawberry Fields that's being developed by Xanadu. So you're also really flexible in that respect. And like, I don't know if one of those vendors here comes up with a much more performant classical simulator of your quantum computer, you can just very easily switch the device and directly profit from the speed up without having to rewrite your code. Or if you want to move from running your code on a simulator to running your code on a real device, that's really just a matter of like changing one line of code, which I think is really a nice feature. And I'm not sure if we have time for that, but I have prepared like some very trivial live demo of the thing to give you an idea how that looks in practice. Well, okay, it says 9 minutes on my clock here, so I think I walked through this very briefly.
Yeah, so you are a little bit into discussion time, but that's fine. And then it's fine.
This would be the last. That would be a conclusion slide, and also this thing here is really short, so I just go through this quickly. So what are we doing here? Okay, we're importing the libraries. Then we're getting a device, which in that case is a simple simulator built on NumPy. But as I said, there's like devices for all those different platforms, and then we're going to kind of construct the simplest possible VQE that you can imagine. Which is just you initialize in 0, you do a X rotation, a Y rotation, and then measure. And like Pennylane, that's another nice feature, uses the natural primitives of Python, namely functions, to represent quantum functions, which I think makes a lot of sense. So there's this function decorator here by which you tell it that this function is supposed to be valued on the quantum computer, and then you just tell it which quantum gates to apply, and then what excitation value to measure and return at the end. Okay. Then we need initial values for those parameters, and then we can already evaluate that circuit at those parameters. And now the Pennylane has delegated that evaluation to the device, and the device has returned a value. So we are very close to like spin up. Okay. It can also compute the Jacobian for you, which is just the derivative of that function with respect to the two values of parameters. And it does that here actually by constructing the circuits that would give you the derivative on a real device, and then executing those and assembling the results together. Okay, and then this circuit, you can just use it in a classical node, which we call here objective function, to do some optimization. And we're going to do this in a very simple way with a simple gradient descent optimizer. This is just an optimization loop, which does like steps under that optimizer and updates parameters. And you can see here that the objective function goes from close to +1 to -1, and the angles change while that's happening. And then we can maybe plot the energy landscape and the path the optimizer took. And that always takes a bit because matplotlib is slow. And you can see the optimizer slid down this side of the slope here. Now, the power of automatic differentiation is that say you wanted to find parameters that wouldn't like minimize the spin, so wouldn't give you -1, but say you would be interested in, I don't know, for example, finding a value for those parameters where the output of the circuit is 0.2, okay? Then you can just modify your objective function, and because we have the power of automatic differentiation, Pennylane and AutoGrad just know how to differentiate that Python code, and that can really be pretty much arbitrary Python and NumPy code in that case, for example. And yeah, you can then see now the objective function goes to 0, which means that the circuit goes to 0.2, and we can again plot the energy surface and how the optimizer slid down the path. And you can see here we started there, and the optimizer found that valley down here. Yeah, so it's a really very convenient way of specifying and training variational quantum circuits. And yeah, it's also a breeze to use if you want to do chemistry, for example, with VQEs. Great. Then yeah, summary. We took this 2 ways of doing quantum machine learning seriously. We proposed this method of adversarial domain adaptation for delineating phase transitions or other classification problems where you don't know where the phase boundary is and where you don't want to tell your network how it should differentiate things, but where you want to be more in a kind of unsupervised setting where the optimizer or where the network is supposed to find out where the phase boundary lies. And yeah, I gave you this quick walk through Pennylane, which is the automatic differentiation-enabled library for variational hybrid quantum algorithms, which is hardware agnostic, extensible via plugins, and very well documented. And I'm sorry for going slightly over time. Thank you for your attention.
Great. Thank you for the great talk and the demonstration. So we have first questions. So Bert, maybe you want to ask yourself.
Yeah, so great talk, Christian. Thank you very much. I'm a bit concerned about the size of the circuit. Is the circuits that you get out of automatic differentiation, are they very big? I mean, you have a gradient computation, so you have n components, so you get n circuits. And is there something to say about the size of these circuits?
Yeah, so the circuits have, for each component of the gradient, the circuits have exactly the same size as the circuit you need to compute the objective function, because really all that happens is that in this one parameterized gate, you're shifting the parameter, and then you have to do it twice and subtract the result. You are of course right that if you have many parameters, then your gradient has many components, and then no matter how you compute the gradient, you have to do many computations. But each individual component of the gradient is just exactly twice as expensive as computing the objective function itself.
Okay.
So there's a question by Roberto. Maybe you want to unmute yourself, Roberto.
Yes, I think it's actually related to the question of Bert. So I was wondering, so here we are looking at finite differences, right? But so, and then you say classically we can do automatic differentiation. So can we do also something similar to automatic differentiation on a quantum hardware?
Yeah, okay. I'm not entirely sure I understand the question. I mean, automatic differentiation in the classical world works by sort of say observing the computer while it's performing the computation.
Yeah, so we need to store something.
And then somehow knowing how each of those boxes can be differentiated, right? And then you do backpropagation through this computational graph. So you construct the graph while you do the computation, then you go backwards through it. That's how AutoGrad, for example, works. It just wraps NumPy into objects that record what is happening during the computation. Now, I suppose you could potentially do this on a logical level if you had an fully error-corrected huge quantum computer and something like data types on quantum computers and some kind of things like object-oriented quantum programming, which are all things that I think lie far in the future, but things should be in principle possible. What is done here is that those quantum nodes, they remain black boxes to the classical automatic differentiation. Just you're telling your automatic differentiation framework what the gradients of those guys here are. So you know, instead of letting your automatic differentiation integrate inside of that thing, you just force it to treat that as a black box and provide it with a gradient. Now, there's a second answer to your question. Very recently, only 2 weeks ago, I haven't played with it, a new version of Pennylane came out where they have a TensorFlow-based device for evaluating quantum circuits. And that device uses TensorFlow to do the computations inside the simulated computations inside the quantum node. And that device, to my understanding, can be used not as a, or if you want to, you can use it not as a black box, but you can use the TensorFlow automatic differentiation to actually differentiate the classical simulator code here of your quantum device. And apparently in some scenarios, this can be faster.
Okay, thank you.
Okay, thank you. Are there more questions that we have? Christian? At the moment, I don't see any. So then let's thank you again for the great talk, Christian.